But my general view is you're all smart and you're going to learn how to use Mongo. I want to tell you about some of the things that we've found in the process of 2 years of using Mongo that can help you succeed. So this is architecture, but we can go into detail as much as you guys want and even drop into a shell if you dare. Okay. So briefly, I want to just explain who Wordnik is so you have some context. We were founded in 2008 by a lexicographer, which I cannot spell still, named Erin McKean. She gave a talk at TED, which was about understanding the meaning of words in context automatically. We patented some technology for understanding what words mean just by reading lots of text. We patented something called free-range definition technology, which means that we can find great examples of words and that explain what things mean. And we've constructed the largest known English word graph. And what is that all for? Well, Wordnik does something that we call discovery. And what discovery means is not search, it's not filtering, it's finding things that are relevant to what you're actually interested in. I'll talk about that a little bit, but I really want to just talk about text and data with you guys. So data, it's all about data. So this is a nice picture of data. We've been using Mongo, like I mentioned, since version 1.2, which is really scary because I didn't realize that how close that was to version 1 of it. I spent a lot of time trying to figure out what to do to get past my SQL's limitations on size and performance, and at about 5 billion records in tables, we had a lot of trouble, and I investigated the solutions at the time, and Mongo won easily. So in the context of data, what does data mean to Wordnik, and why do we need lots of data? Well, that word graph is built by data. It's built by data by consuming text across the web very fast. And it also means that if we need to use the word graph, we need to query it very quickly. So we have a lot of data that we need to get to in real time because we want to know things like the difference between downtime as an alert and downtime as vacation. Right? So what happens is we consume text at rates between 5 and 50,000 words a second. They go through our NLP pipeline. We extract the meaning of them. They go into our graph, and then we get to use it. So what does that mean as far as size? This thing has like 50 million nodes. It has 80 million edges. We can get into it at 80 microseconds, which is really fast. And this is all built on MongoDB. I did a presentation on how we built it. It's a very specialized use case, but MongoDB was a great solution for this. Right, so what do we actually do with it? So with data at Wordnik, what we do is we update this graph constantly. And by using the graph, we augment our natural language processing pipeline. And we do what I call reality-based annotation, which means that we use current real-world data. Because the problem with text and language is that it's just not static. So if you take something like Twitter, there's hashtags which have specific meaning in the language or semantic value. Tumblr, which just has crazy random shit. WordPress, like anyone can publish anything, right? And you never know, right? Something's going to show up on WordPress that's going to redefine what, I don't know, big data means or something like that. We don't know what's going to be next. So we have to process a lot of text to understand what words mean. And without that, you end up with outdated data, which gives you a problem. So is a 20-year-old corpus good enough? So we say the answer is no, because like Justin Bieber's not even 20 years old, right? So if we didn't know anything about him, and we didn't have a graph to query for information about what Justin Bieber does, we might miss some really important facts, like he's a Soviet Kanakistan, right? Right. So in any case, we think data is really important. We rely on Mongo for over 99% of our data by volume for all of Wordnik. Okay, cool. So how do we do this? So like many people who have come before us, we are an EC2-based deployment. And we actually were on a physical data center and switched back to EC2, and I want to go into the details of that. And we ran into trouble with elasticity on physical data centers. So spinning up a new server, 6 weeks, $1,000 for a server. You want another data center, you got to pay twice as much. So the same things that make the cloud vendors really excited with advertising. So we do our horizontal scaling basically by adding servers. I want to go into that, and this should play into how you think about Mongo, at least how we think about Mongo. But of course, we can always go vertical. I'll never say that a virtual server is nearly as good as a physical one. but they sure are a lot more convenient and a lot cheaper. So yeah, at some point, I hope we're really big and we have thousands of physical servers to run stuff 10 times faster. But in the meantime, we have lots of lousy little VMs. But let's go, so blah, blah, let's go into the details. So we follow this paradigm that I stole from Netflix, or someone else probably invented it, but I heard it from them, at least it resonated the most, called microservices. And the idea is that a service is like a standalone building block. It's something that performs a very specific function. It's kind of like 20 years ago when we were programming in Java, you have jars, and the jar is a library, and the library does one thing. But we've taken it to the next step, which is saying it's not a library, it's a service. It's an actual server that runs, and it does one thing really well. And the nice thing about doing that kind of architecture is that you increase your overall capacity, if you do it right, to adding a more like this button, which means I have services, like here I've got a service that's a word graph and a glossary or user content, and I just add more of them, right? The service is a server, I launch another server, they get in the grid. I'll talk about the arrows because that's an important part to how services actually communicate. But that's our scaling motto, is like a whole bunch of little servers. So if you think about what you might work on or you might have worked on previously, or what I used to work on were these monolithic applications. If you think of it as a factory where everything's in there, it's like Foxconn, right? And then we break it up into all these little tiny things, right? Something that makes the LCD display, the buttons, that sort of thing. Everything does a really good job. The problem with this big factory model is that once you run out of real estate, right, you run out of RAM or something like that, you can end up in a lot of trouble, right? So Foxconn can keep getting bigger maybe. At some point they run out of real estate, they can't do it. So you should outsource stuff over to small factories. So you can stand back and say, well, this sounds like service architecture, service-oriented architecture, right? Like late 90s, 2000, like lots of jokes about SOA. And it's kind of like SOA, but it doesn't have all these ugly diagrams. Like everyone has seen these things. This is terrible stuff like no one ever wants to relive. You guys might be too young. I'm old enough to know that this is just something that was just a mess, right? 1999, 2000. This, go away. This stuff, go away, right? This, go away, right? So this is not POSOA, which I'm calling poor old SOA. We're calling it microservices. So it's different. There's no proprietary message bus. We talk REST. Oops, one step ahead. The objects are decoupled. The storage is dedicated, which is what is the important part now, and that's what you guys came to talk about Mongo, so we're going to talk about that. And in our architecture, we don't care what you develop your services in. Is it Java or Scala or Ruby or PHP? It doesn't matter. It just has to be compatible. It has to communicate. Right? And so you might say, well, speaking REST, like, that's kind of lame. It's kind of slow. People fight over nouns and verbs and REST semantics and, being proper REST and that sort of thing. Like, these are all valid ways to delete a pet, right? Pass a query param, delete. Pass an HTTP verb, delete. Post an empty, right? They're all valid. So what do? You have like a peer review, API council, style guide that no one ever reads, better docs, right? So this world sucks too. So we say that like the problem with this architecture, and I promise I'm going to get back to data, is that communication is hard, right? Because you have to have things that know how to talk to each other in common format. You need to have a contract, right? So like when I say delete pet, someone's not gonna come back and say, well, we renamed that method, right? You follow redirects or something like that. You don't want that when you're calling thousands of times. So we use that as a driving force to create this thing called Swagger, which is, you might have seen this. This is a screenshot of a UI, but what Swagger is, which drives our whole framework, which I promise I'll get to data in just a minute. Swagger is like this framework that we built for declaring and documenting APIs. The framework will, we also released an open source framework that auto-generates a spec. We also have a library that generates clients and then a JSON-based test framework. So it's all open source. You can look at it with pretty logos. But in the end, me as a consumer of a service, like I'm writing code and I need to call something to get a pet or delete a pet or add a node to a graph or delete something important, we have a code gen. So basically, the services declare what they do. We call this code generator. It generates code statically. and makes a contract. So now if I want to get a pet by ID, I call this URL, I call this method. If I'm in Ruby or Scala, it doesn't matter, right? So the idea is that the Swagger generates this contract between client and server. Clients then become functions that you call. You don't care, like this get pet by ID, that might be a path param or a header or a query param or God knows what, right? Post body, doesn't matter. Like consumer doesn't care. Consumer just wants to call the thing and get a pet, right? So we built this thing to do this, right? So in our workflow, we have Jenkins, which builds a service library, builds a service application, builds an RPM, builds a compatible client library, and then the consumer just declares a dependency on that client library. Now they have access to do that. Right? Now they have access to call it. In our service framework, we have ways to deal with compatibility and versions and clusters and stuff that I can talk about afterwards if people are interested. Okay, so I promised I'll talk about data now. So one of the things that we figured out to do that helped us a lot, which is this is a Mongo thing, it's actually a general data thing, but is microservices. We give them smallish databases. We share nothing across them. We use replica sets. So the idea is that a service has all that it needs to run on its own. And sometimes it feels like that can get in the way, but if you design things the right way, share nothing is actually a great thing. It gets the scale better. We deploy to ephemeral storage. That sounds crazy. I'll talk about that in a minute. And we keep everything really small. That's by design. So that's one of the tricks, right? It's like, how do you keep your database small? You have to plan ahead and you have to think about things. So in this pretty picture, word graph service here, there could be one or many, has a primary, secondaries talk to each other. It's just the replica set world, which is great. So now I'll talk about how we keep them small. This is one of the most important things that I've run through. There's really easy tricks that you might have heard. So Mongo's schemaless, right? Every single record in a collection can be completely different. I mean, you could have every record you could have a pet and a user and a document and a car all in one place. It's like a kitchen sink, right? So the problem is that it's not really schemaless. It's like you have a schema for every document. So the problem that you end up with is that the size of the field names that you use actually makes a difference. So if I have something like this and I'm adding user underscore name equals Tony, and then I get smart and say, wow, I could save some space, put UN equals Tony. If you do this 10 billion times, this can make a significant difference. And it did. We did this with all of our data layers. So the next thing is indexes, right? Indexes can get giant. The ID field is a field that's indexed no matter what, unless you bust Mongo, which I could talk about that too. But you get it. It's indexed no matter what. If you don't want an index on it, it doesn't matter. You get an index. So you might as well make it matter, right? So in this picture here, this is one of our collections that had, I didn't show the number of records. I mean, there were like 15 billion records or something. This is 100 gigs of index, right? 100 gigs. If I've got a 500 gig disk, like I've just blown 20% of it. And in this case here, this ID index, you don't have to do the commas here. This is 50 gigs in the ID field, and then there's this other index of 50 gigs. Actually, it turned out that we could get rid of one of those. That's 50 gigs of disk. That made me really happy. So if you can actually make the ID field useful, you can save yourself a lot of disk space. And then I'm going to explain another thing that it can help with, which is in the replication process and backups. So keeping them small by making the ID field matter. Okay, so let's talk about the ID field and why it's important and why you can actually do something useful with it. So Mongo uses B trees, I think for all indexes still, where you have this thing that looks like a triangle where this would be a current record and then there's a less than or greater than on each side. And so the idea of having the right biased B tree means that this area of the tree, like then all the numbers between 15 and 27, this could be your working set, right? These could all be on disk and you never access them. But the way Mongo is so efficient with memory, it will keep the working set in memory. So if you can actually keep your index hot on one side instead of having random reads across this, then it doesn't even matter how big this thing is. This set can stay in memory and your system will run fast. So you don't just want to make it an auto increment like you used to in MySQL or you still do in MySQL. Do something, you're stuck with it, so you might as well do something intelligent. So if it's a user collection, use a username. If it's an email collection, put the email address. It doesn't matter. You can override this thing. You don't have to use the canned object IDs that come with Mongo. You can override the thing. if it's date driven, right? Why not have something that has the date in it as your unique identifier? Put milliseconds or microseconds or whatever. Then you can search for all logins that were from, that happened in May, right? So there's things that you can do that end up being very clever and will save you a ton of space on disk. I think that, like, I don't want to contradict what I'm saying. Like, I think that in general you should be lazy until you can't anymore. But you can spend like 5 minutes thinking about this. Say, I don't need to have references to other things, or I don't need to just waste this ID field below 50 gigs on this. I guess you make something meaningful in it. So whenever designing collections, we always spend a bunch of time making sure that the ID field is used as well as possible. Okay. What else about this? So I have the saying, DAO or die, which means if you're going to do something crazy on your index scheme, you better make a data access layer so that people aren't going to mess up, right? So if you have some kind of index scheme that uses regular expressions, the last thing you want is for some knucklehead to forget to do a starts with here on this ID, looking for downtime, and then have to scan 500,000 records, right? So I did that. So I'm the knucklehead. So look, it's super fast. I mean, this is great. Like 680 milliseconds for 500,000 records. But that's wrong. Like, you don't want to do that. You want to have control over how you access the data, or someone's going to crater the thing. I mean, you don't want to have, we literally had somebody, I won't tell you who it was, query like this table with, like, I think we had 20 billion records in it, and he didn't put a starts with, and like the thing just went berserk, right? And this was in the early Mongo days. They fixed it since then. But the thing crashed. Like, we had like pagers going off because of that. So part of my philosophy is spend a little bit of time, build a data access layer, protect yourselves from doing something silly. Don't have like a method where you can just pass arbitrary queries into big collections, or you're going to end up getting woken up by someone doing something silly. Like, this is the right thing to do. Like, if you put this here, starts with, in this regular expression, number of objects scanned, 4 time 0 milliseconds, right? That's how things run fast, and that's how we get 80 microsecond reads out of our graph with 50 million records in it. So you've got to control this sort of thing. Like, this makes everyone happy. The other thing is sharding. So we're a little unconventional. We do our own sharding. Spend a little bit of time. It's very easy to shard. You don't have to go crazy and set up a bunch of servers. Building your data access layer will save your ass if you have to shard. Because now when I'm just looking up for a particular user, I'll just add another method to go and find the right shard, the right host. In fact, I can add another one of these without disrupting the clients. Don't make your client code, don't make them do this, right? That should be in your data access layer. And so sharding, whether it's internal in your application or if you use Mongo sharding, building a data access layer, it sounds like, I mean, I know that over abstraction is worse than premature optimization, but I think that spending a little bit of time on this sort of thing will keep you healthy. Someone's sleeping already. There you are. Okay. Lastly, so why keep them small? So this got me the other day. We had a database that was not that big, like 300 megabytes or 300 gigabytes, something like that. These things will all give you a good reason to keep databases small if you can. Starting a new replica. So in the process of starting a new replica, Mongo does some clever stuff. It doesn't create indexes and then add records. It adds records and then creates indexes. That means in one fell swoop, it has to build an index on however many records you have. Okay? I ran into a surprise, which was Mongo's great with memory, but when you do an index rebuild, you need to fit that whole index in memory. So running these servers, these M1 large servers, only have 8 gigs of RAM, everything's happy. Start up a new replica, pulls in 40 million records, does a sort, OM killer comes, right, takes out the server. So it matters. Like the initial sync of a database, there's clever ways to do this, and I'm talking about this on Friday up in Mongo SF. But there's clever ways to do syncs, but when you do initial syncs, you have to wait, right? Backups, it's the same thing. When they're big, it just takes longer. This is not rocket science. I mean, I don't know if there are many Mongo admins around, but I've stared and looked at these things for a long time, just watching. Tick, 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 60% still, right? This is not that much data. 600 gigs, something like that. I don't know. It's not a lot of data, but sitting there watching that while something is down is a real bummer, right? So the shorter, the longer, yeah, this can take days. The longer you have to wait on this, the bigger issue you're going to have. Someone's going to be down and upset. Everything is easier, I feel, when things can stay small. Your total cost of ownership will go down. So like having smaller servers, I believe that for all of these reasons, having a bunch of small servers that, rather than one ginormous EC2 server is just cheaper, right? Okay, so I want to talk about ephemeral storage because I said that we run that. And it's kind of strange. So every EC2 instance except Micro has ephemeral storage. The bummer is that, like, if you use their GUI, like EC2 console, you can't access it. You have to use the API. One of the things is that, like, people don't really know what Amazon does behind the cloud, but it's basically been reported through one or other source that the ephemeral storage is actually on the server that you use. EBS is over a network. EBS has issues every now and then. I think it's fantastic. It has this enormous cache. It's very hard to benchmark between EBS and ephemeral storage because of the size of the cache they have on it. And I generally feel that it's faster, but again, how you do your benchmark, you get whatever result you want. And it's included with the cost of the server. So when you launch a large server, you actually get like a terabyte of disk, right? If you do it from the console, you don't see it. If you do it from an API, you can get access to it. But the bummer is they reboot your server, it's gone. Right? The data is gone no matter what. So what do we do? So you obviously can't just have data go away. So what we do is we'll have, for instance, in two zones, a service here. This one's called a word graph service. The writes obviously go cross-zone from this one here, from 1C to 1A, to a primary to secondary. And then somewhere else, usually in one of the two zones, but sometimes it's in a different region, you put a secondary up and you make it hidden with no vote. And what that means is that, and it's on EBS, right? So what that means is that all these things can die, and it will never become a primary. Okay, your system's down, right? But at this point, you have other problems, like if all of Amazon goes down. But in this case here, it's basically going to apply the write operations or the inserts, that sort of thing on the secondary, which is EBS backed, which you can do nice things like shut it down and snapshot it, or use LVM to snapshot the data, or that sort of thing. So we basically have this model where, okay, these servers, they run these databases, they're just, I mean, they go away, right? Including the data goes away. But you always have one that has the ability to be cloned, to be restored to another machine. Right? Another thing here, so if you're multi-zone and you have a DR site, so in this case we'll use the East Coast as a DR site, then we'll maybe have the backup server in that other zone. And then we have an arbiter, which I misspelled here. The arbiter will sit in the DR zone, because one bummer would be, like, what if this thing dies from the connectivity point of view, but the servers are all running, right? You don't want to actually have these things participating. So this guy will then decide who the primary is to keep the hot side running. So having an arbiter in a separate region is a good idea. Having your data go across two regions is a good idea. Yeah, so if there's a connectivity issue, then the arbiter is going to decide which one it should actually go to. I haven't asked yet. Anyone have any questions? Yeah? No? Okay. So let's talk about how this really works, right? So we were on 3 DAS devices with, like, I don't know, like 150 disks or something like that, 18 terabytes. And we went to 21 large servers and a couple of extra large instances across 3 zones using 2 regions. We cut our costs for running this thing from like $18,000 a month, which is a lot, down to like $5,000, right? So bringing it down, this helped. Now we just keep these things at capacity. You don't have this monster server. Again, like, we can go back, we can have faster servers to take up where my engineering skills fail. But in doing this, it was just cheaper, right? Now it's tricky because it doesn't do you any good. Like, let's say that you've got these physical servers and they've got excess capacity, and I mean, you're wasting money. But if you've got VMs running and you have excess capacity, you're wasting money. So the trick is to maximize every server that you have running and spin them up when you need more capacity. I put a blog that went into much more details about it as far as how software architecture, which we've kind of covered briefly, has to actually change to take advantage of disposable servers. Right. As for the service tier, so right now we run probably 1,000 requests a second during working hours through our service architecture. They're going. We use a WebSocket connection direct to the consumer, so we see these things and we get pretty graphs like this. This was during the day today, 208 calls a second, right? Every single, and this is just from the consumer, right? Behind the back, in the back end, like all kinds of stuff has to happen. So we end up with these big, impressive numbers. But everything has to go through Mongo. Every single one of these calls, every second is going through Mongo. There's nothing cached for a number of these things. Everything is logged. Everything is doing a read or something like that. So in our framework, Mongo is scaling very well. Right now, we're in the process of, we released something that basically sits on top of this Swagger framework called SwaggerSocket, which is a sub-protocol which sends the requests over WebSockets. And we get like a 25% speed increase off the bat because of HTTP overhead and garbage that it spends, which is, I mean, REST, let's remember, is completely synchronous. And I don't care if you're using JavaScript and you get callbacks, it's still a synchronous request response cycle. The thing with using a WebSocket connection is that you can actually do full duplex communication. So you can actually send and receive simultaneously. And so in those scenarios, we're seeing 100% plus increase in speed because the server can actually be sending and multiplexing and batching requests back to the client. There's a number of things that will be coming out that use that socket framework directly to clients and then give this discovery thing that I talked about earlier directly to people. I'm getting to the end. So my pitch for Wordnik, if you're interested in Scala, tools for developers. So this is from we have a product called Caprica that we use internally. We might open source. It manages all of our servers. We launch them, see in this case here, 10 clusters. So that means there's 10 uniquely defined, separated clusters of servers that shall not ever communicate with each other. It manages our configuration so that when I need to talk, I'm a production cluster. I need to talk to the database. I always know who to talk to. That's how we keep this thing running without an IT guy going crazy. We have no IT people at Wordnik. If you want to work on WebSockets, finding needles in haystacks, Swagger, Mongo, of course, then we're in the Bay Area, which is different, but we'll relocate people. So come talk to me if you're interested. Yes?
You had another service, Wiggle or something like that? Am I remembering it wrong, or was it only Swagger?
I think you remember it wrong.
Okay.
Yeah. It's a Swagger and Wiggle. You got the W, the G's, yeah.
But I remember seeing some cool like front end.
That's probably this thing that you're thinking of, yeah, Swagger framework. So if you want to see more, here's some links. A developer site that that shows a sandbox to our API. Swagger, which is our framework. There's a bunch of stuff on Wordnik, on GitHub, which apparently goes to my Twitter feed, which I didn't know. Questions? That was quick. Yes?
So I'm just curious, you have this graph.
Yeah.
So are parts of the graph distributed across these different servers, or?
Yeah, it's actually 50 million sounds like a lot, but it's actually small enough to fit pretty easily on one server. We have them running distributed for performance, and we also use it not only as a service, but some of the NLP stuff has to call it like 100 times a second, that sort of thing. So we'll actually run it in memory also.
So you're like if it gets bigger, your plan is to go to bigger machines, or?
Yeah, I haven't thought about that yet. No. It actually, it's very easy the way that. So we very tightly control the access patterns to it. So like finding an edge starts with filters, that sort of thing. Since we know a lot about the language, we've done a very good job figuring out the distribution of letters and how we should split across. So we've actually sharded very similar things to 100 shards. We'll do the same thing with this when it gets too big. Yes?
I was just curious, since your system is essentially a graph things, did you evaluate any graph databases like Neo4j?
Yeah,
so
yeah.
What are the motivations behind that versus Mongo?
It just was so much fun to build. No, We did. So the thing is that our use case is very different from like a map. So Neo4j is like an awesome Java-based graph database. It's really good at routing things from like A to B, regardless of how many turns you have to take if you're thinking about a real map. In our case, it's more like, I'm here, what's 3 hops away from me? And in that use case, this is just way faster. Yes?
Small is relative. Small to you might be big to me or vice versa. How did you determine your optimal small?
Oh, that's easy. The cheapest real server from Amazon until recently was a large, because it was 64-bit. And it's like $250 a month. And that gives you like, I think 950 gigs of disk. So that's our small. That's the smallest we go. And now they have small, like literally small and medium servers, so you can get smaller than that.
One question. What do you use to crawl your data? Like to crawl the sites?
Oh, it's a lot of work. So we use, I'd say that we use, the framework that we use the most is Tika, Apache project. Yes?
Just one more question, I guess. So you mentioned that your databases are like hundreds of gigs in some cases. And so, and obviously these machines don't have that much, and obviously Mongo likes to have stuff paged.
Yep.
So I'm just curious, how does that work when you have is your working set basically close to the memory of the server, or does Mongo do large paging?
That's a great question. So the question is, what do you do, I'm summarizing, what do you do when your working set is out of RAM? Okay, so the biggest issue that I've run into is not when your data set is out of RAM, is when your index is out of RAM, right? When your index is out of RAM, you're screwed. Like things you just never know, right? So the trick that we have is that we always want to keep the index in RAM, at least the working part, right? So that means that if this whole triangle is an index, if this working part is in memory, then it knows directly how to get to this spot on the disk, and that has been plenty for us. Right? I mean, previously we had these monster servers where, we have like 20 billion records, and it was like 4 terabytes in one database, and so there's no way it's ever in memory, but it was fast enough because the indexes were actually always hot. Yes.
It seems your data is relational between words, how words relate to each other. How do you design your schema, since Mongo it's not relational?
Yeah, trial and error. So we started, like I said, we started on MySQL, and we because this is like 2-something years ago, which is like a long time in computer years. We mapped stuff literally from MySQL to Mongo, and got it working, and it worked fine. And then we kind of realized, like looking at this index stuff, and we got this ID fields, and they're actually work to create, right? So we just started this evolutionary process. It's a function of like your access pattern to the data, how frequently it changes. I mean, it just really depends. Like the domain of the data really depends. So in many cases, we just have lots of records, and they're just they are relational in the sense that, yeah, this is a word. Right, and so like it's very lucky to be able to use words because they don't change, but it just depends on how you access it.
Is the schema for your records consistent?
Yes, never ever have multi schemas in one collection.
How do
Ever.
you handle when you change the schema? How do you handle migration?
Good question. So basically, the question is like, since you can have whatever you want in the database, how do you not end up with everything in the database? So when we do this sort of architecture, when we have versions of services that become incompatible, then we'll launch new versions of the data. And it is the job of the new service. So let's say that I added a field or changed the data type. The new service has to be aware of both formats of the data, right? So it's like a switch, which is lame. Or we find a way to actually clone the data and then slowly migrate off of it. But we never, ever have two different formats. And it's hard, right? Because then you want to update. You don't want to do migration scripts and that sort of thing. Because that's one of the promises of non-relational and schemaless documents, is that you don't have to worry about it. But in practice, we found that, like, yeah, somebody puts in a puts in something, they think it's an int, but it's really a long, and then they go switch the code, and now they start putting a long, and they get it from the driver, and they cast it to a long, and it's really an int, and it blows up, and just bad things.
And I think it's insecure too if you've got all this, you don't even know what the hell is
Yeah.
half the time. I think you're opening security vulnerabilities.
It is.
That's a great.
It's definitely possible. Yeah. Yeah. I don't want to sound like too freakish about the DAO layer, but I've had too many nights where I was up all night because of stuff like that.
How you are managing that reads versus writes, like data integrity?
How do we manage that?
Okay.
So in the case of how do we make sure it's consistent?
Yes.
So the trick is that like we have a DAO layer and we have a connection manager. The connection manager, when the server starts up, it asks like who do I talk to? The server says, okay, you talk to this host, it's a replica set, and it goes and figures out all the reads. So in our DAO layer, we have when you go to get an item, let's say it's get user, right? It will actually say, I want a read-only connection or I want to read-write. So at that stage, you basically, the client being the person who wrote the DAO, the developer, gets to choose if they don't mind if it's eventually consistent data. So like it's really at that layer that you decide whether you need a read-write. If I need something that's consistent, I'll just say, I need a read-write data connection. In which case, then you start potentially overloading your master. So we try to make it so, unless you absolutely have to, get a read-only connection. And then, of course, like in the case of replica sets, the driver can actually say, I need this kind of consistency at the W factor, the right factor. So you can do that also if you do like update password, and the user logs in and it's like invalid password, they're all pissed off. Anything else?
And what do you shard on? How do you know that this shard?
God, it just depends on the data. So in one case we had collections that were basically keyed off of words, and so we knew that we had to shard on the word, right? So then when you say, okay, well, I need to insert or I need to fetch this record. Where do I go? In my DAO layer, I say, okay, well, what is your word? The first 4 characters fit into this bucket. You point the client over there, and then that's where they live. Okay. Anyone wants to talk more about any of this offline, or if you want to move to San Francisco, if you're really smart, please come join me. Thank you very much. Yeah.
Just wanted to so we had Aaron McKeon speak from Wordnik at the LA Semantic Web meetup, and it was a great talk from like the user side. So it's definitely worth looking up that TED talk. It was a really cool story. And
yeah.
Obviously it was a great talk about.
Yeah, she's a much better speaker than me. Yeah.
No, this was really great. But anyway, just wanted to add that plug in.
Thank you.